Good morning and welcome to the Open Systems Media webcast, Powering the Edge of the IoT. It is all about efficiency, but you already knew that, right? This webcast is sponsored by DigiKey and PowerFilm Solar. My name is Rich Nass and I will be your moderator for this webcast. I'm also the Executive Vice President of Open Systems Media. I lead the embedded and IoT teams for embedded computing design. If you are not familiar with that property, I suggest you check it out because it is a great resource for anything related to the design of hardware and software for embedded systems. You can find it at www.embeddedcomputing.com. It's filled with design articles, white papers, videos, blogs, podcasts, and lots more. So back to the subject at hand. On this webcast, we'll be talking about power efficiency, obviously. But if ever there was a misleading specification, this is the one. It's so application specific that when you ask the question, what is your power efficiency? Almost always the answer is, it depends. And the IoT comes with its own set of needs for power level, operating environment, and the technology that's deployed. So on this webinar, we are going to educate you so you can make your own determination on what's best for your specific system. On this webcast, you'll be hearing from Martin Schulte-Holbein, a manager and field application engineer for Digi International. Martin joined Digi in 2007 as a field applications engineer. He leads the technical, embedded, and RF team in the EMEA region. At Digi, he provides pan-European support to sales, distribution, and customers in evaluation, solution development, and deployment of embedded and RF products for wired and wireless applications. And then when Martin is done, you'll hear from Sam Jones, a research and development engineer from PowerFilm Solar. Sam has been the lead engineer on dozens of photovoltaic energy harvesting solutions, focusing primarily on applications in the IoT space. Sam's work in indoor light harvesting has helped demonstrate that solar and photovoltaics can be a vital component of the total power solution almost anywhere. Before I bring out the two speakers, let me go over some of the housekeeping stuff. The entire presentation will take about 40 minutes, give or take a few, and that'll leave us plenty of time to answer your questions. We will answer as many as time permits. You'll find on the console window an area where you can enter your questions in real time. And as I said, we'll address as many as time permits when we're done. So we tend to answer them in chronological order, so I encourage you to ask them as you think of them. Don't wait until the presentation is over to put your questions in. If we do not have a chance to answer your question when we're done, somebody from one of the two companies will get back to you with an answer. So every question will be answered. It just may or may not be as part of the presentation. If you have a question pertaining to the operation of the webcast, like if the audio doesn't sound right or the slides are not advancing properly, put that into the question box and one of our technical folks will get back to you with a fix. There's a maximize button that allows you to see the slides in a larger window. And when we're done, this webcast will be available in an archive version. So if you want to go back and review, if you want to forward it to a friend or a colleague, it'll be there for you. That's about all I got. So let me now hand it off to our first speaker, who is Martin. So take it away.
Thank you very much, Rich, and welcome everyone to the session. Let me first give you a quick overview of today's topics. After a short Digi International introduction, I will start by discussing the different terms that I'd like to talk about today, mainly power management and power efficiency, and explain what they mean from my point of view and how they relate to each other and why they are important in many applications. Second and main part of the presentation will be to talk about the different tools and options that are available for power management in IoT systems. And I will conclude the session with a brief overview of the Digi embedded product portfolio, the Connect Core system on module solution that supports all the power management features and options I will explain today. Digi International is a 35-year-old company based out of Minneapolis, specializing in products and services for customers seeking solutions for IoT applications. We are organized into a number of business units, each offering a range of products. the cellular routers and infrastructure management business unit, offering off-the-shelf devices for enterprise LTE and infrastructure connectivity. The OEM solutions business unit, offering a wide range of embedded system on modules with built-in wireless connectivity and security, and RF communication modules, supporting various protocols such as short-range RF, LoRaWAN for LTE for IoT connectivity. And complementary to all of our hardware products is our software and services offering, including a vast amount of development tools, and DigiRemote Manager, a cloud-based device management and IoT communication platform. Finally, overarching our complete product portfolio is TrustFence, a ready-to-use over-the-air upgradable security framework. Digi's mission is to simplify and accelerate the development, deployment, and management of secure connected devices. We help our customers to save time, money, and risk, and service them relentlessly to ensure their success. Our OEM or embedded product offering consists of the mentioned ARM-based embedded system on modules and single-board computers. We use NXP's IMX application processors and additional wireless components, and the XB RF communication modules, providing a common form factor supporting multiple RF technologies. If you are designing products for industrial, medical, or other demanding applications, both power management and power efficiency can be differentiators. Power management is the practical process of controlling power use in a system by hardware or software. For example, actively or automatically disabling an unused system component with a goal to save power. Power efficiency, on the other hand, is a measure officially defined as the ratio of power output to the total power input provided to a system. And I would personally add useful power output and define this in the context of an IoT or computing system as the feature set a product can support with a given power budget. For example, connecting a display, camera, and other internal or external components of a system. This is one of the key parameters in any system design and integration, and especially critical for mobile or size-constrained devices. We will hear about that a bit more later. A common goal in product development is to optimize the power budget to support a required feature set and/or to utilize less energy to perform the same task, eliminating energy waste. As a summary, power management is a practical approach to increase power efficiency. Why does power efficiency matter? One obvious reason is it can help to save the environment and reduce greenhouse gas emissions. Another key point is that it can help to lower operating cost of products due to lower power consumption and other benefits. Many applications have a definite need for power efficiency. For instance, in an industrial application, the OEM may have a fixed power budget. By maximizing the efficiency of that system, more compute power can be integrated and additional features can be deployed, but only when needed. Alternatively, in a medical or transportation application, size may be the most limiting factor. Hence, by running the system more efficiently, you can reduce the number of heat sinks and fans and other components because less heat is being generated. And at the same time, a smaller power system would be required. This can even lead to increased safety and reliability of the device. In an untethered medical application, such as a card-based product, mobility of a system may be required, which would define the need for a smaller, more agile platform. This choice is far simpler if the system is lighter weight or designed for extended operation on battery power. As you can see, there are many direct and indirect benefits of higher power efficiency. So let's have a condensed look at the most relevant. Battery life improvements, improved thermal behavior and temperature reduction, reduced product size and cost with fewer moving parts, smaller batteries, and power supplies, and overall smaller enclosure size, increasing the potential mobility of a device. Noise reduction and improved reliability, increased product lifetime, and better mean time between failure. You may have noticed that MTBF values are typically provided with a specific temperature value. Lower temperature typically means better MTBF values. Power-efficient systems typically provide a set of features for power management to ultimately maximize their efficiency. I will discuss each of these power management practices individually on the coming slides, pointing out in which areas the DigiConnect Core solution has unique benefits or provides added value. One of the key advantages of using system on modules comes back to power efficiency, in that the SOMs permit the use of power domains. This means that the SOM can be handling the majority of the processing for the application, thereby allowing most of the remaining components, either on the SOM itself or on the baseboard, to be shut down or significantly power reduced. For example, reducing power or shutting off wireless components or even I/O that's not being used. On multi-core or heterogeneous compute systems, it is often possible to extend this principle to allow control over individual CPU cores. Further examples include a cellular modem or memory that's external to the module. While each of the power gains may be minimal, when you add them all up, their sum becomes significant. Dynamic voltage and frequency scaling, or DVFS, is a feature of modern computing systems that provide automatic adaptation of CPU frequencies and voltages according to the actual system load. In the Digi solution, this can be fully customized per CPU core using predefined templates. And in addition, DVFS can be applied to the graphical processing unit as well, further increasing potential optimization of power efficiency. Another feature to mention is the boot mode configuration. Traditional embedded systems are fully powered as soon as the power supply is attached, typically. Providing a power key can help to significantly reduce power consumption when the system is not in use. The Digi solution offers a configuration option to switch from boot on power, to boot the system as soon as power is applied, to wait for power key, to only boot the system when the power key is pressed, and vice versa. That's right. This goes hand in hand with sleep modes, the ability to send the system into various low power states with different power consumption levels for different use cases. These low power modes can typically be set up using either software or hardware configuration, and can often be activated by an application or system call, or by using buttons or similar functionality. In many applications, for example in a vending machine or a parking meter, a fast wake-up time from a low power state is required. You don't want users to have to wait until the system has fully booted the operating system in these use cases. Suspending the system to a self-refreshing RAM allows short wake-up times with relatively low power consumption. Digi has optimized the solution to achieve ultra-fast wake-up time in the range of a few milliseconds. If wake-up time is not the most relevant aspect in your application, you may want to opt for lowest power consumption instead. However, in most applications, simply cutting power is not sufficient. Often you want to maintain at least a clock to keep date and time, or offer more options to restart the system other than just attaching power. Many systems offer a power off or RTC mode to provide this functionality with as low as possible power consumption. I'd like to provide some practical context here with actual values, which are just rough indications for you to be able to understand the magnitude. A typical system on module based on an NXP IMX processor, for example, that normally consumes around 500 milliwatts under heavy load, for example, while decoding a video, could consume around 10 milliwatts in suspend to RAM, keep in mind you still have the ultra-fast wake-up, and less than 10 microwatts in power off or RTC mode. This is the practical trade-off between fastest wake-up time and lowest power consumption. And of course, you can combine both options as needed. Okay. Efficient systems provide several sources for wake-up events that can be used to resume operation from any of the low power states. One of the most common wake-up sources is an interrupt-capable GPIO, which can be toggled using an external component, and the most simple approach would be using a button or switch, but it can be used for more sophisticated logic using an external microcontroller. Another very common option is to use the real-time clock simulating a timer. If the system offers one or more tempering pins, which are normally used to detect external unauthorized intrusion into the system, for example, an attacker trying to open the enclosure, this can be used as a wake-up source as well, to allow the system to react to a security breach, even while being in a low power state. In general, it is a good approach to utilize the component with the lowest power consumption in the system for power management tasks, if possible. Many developers add external, very low power microcontrollers to outsource power management. Digi adds an additional low power controller we call Microcontroller Assist, or MCA, onto the SOM, but external to the actual processing cores, which can be utilized for power management. For example, this MCA provides GPIOs, tempering pins, but also a serial port as additional wake-up source. The system can be configured to wake up on a magic word coming in on the serial interface of this MCA. The power key is another useful feature we discussed earlier, as it offers the option to utilize different boot modes. Wake on LAN as an option to wake the system remotely over a network is available on many systems, similar as with the serial interface, using a magic word or pattern or arbitrary data to resume normal operation. And finally, waking up from a low power state using wireless is still not very common in many systems, as it requires the RF component of the system to be powered in some way. Digi has recently included Wake on Bluetooth on its devices, which is a nice addition to the list of wake-up sources, adding additional options for applications to interact with devices operating in low power states. Most of these features typically require lower level system access through a command line, or at least require configuration on operating system level. A user-friendly IoT system should provide a mechanism to allow developers to utilize power management features from within their application code. Digi has added a programming interface called APIX to its operating system offerings, allowing programmers to access many of the embedded hardware interfaces of the system. And in addition, this set of APIs also provides high-level access to power management capabilities. This can be used to control, for example, CPU and GPU frequencies, disable and enable CPU cores, set up temperature management templates, and so on. Another point to mention in the context of power management and efficiency is the scalability of a system. If you are using an IoT solution that allows you to easily scale from lower performance, lower consumption devices to higher performance devices, it can potentially help to achieve the most power efficient implementation for a specific application, while having options to increase product functionality or further optimize efficiency in the future. Many compute solutions today offer heterogeneous architectures with multiple CPU cores in different performance and consumption levels, such as ARM Cortex-A, Cortex-M, and so on, which can be individually powered as needed. This allows for very efficient system implementations. Ideally, the software offering in such a system is optimized to use this hardware advantage. Digi is offering such a solution with its Connect Core system on module product family in both software and hardware. Our range of SOMs scales from a single core Cortex A7 on the lower end to dual or quad core Cortex A53 in the mid-range and a dual or quad core Cortex A35 with advanced multimedia capabilities and many industrial interface options on the high end. All of these are specified for industrial temperatures at -40 to +85 Celsius. And all of them provide an option for an integrated pre-certified Wi-Fi and Bluetooth radio. Bringing it all together, we take a systems approach to integration, and we call that hardware-enabled software-defined. In addition to highly integrated hardware and software, we have a suite of development tools that further simplify common design activities. We partner with leaders like NXP, Microsoft Azure, and AWS to bring more complete solutions to the market. And we have a global support team and in-house design services division to help customers no matter where they are located. Digi Connect Core is providing a highly integrated hardware and software solution. We provide industrial-grade hardware designed and tested to work reliably in harsh environments with demanding requirements. We enable customers to scale from single-core devices up to quad-core high-performance devices with commonalities on the form factor, all supported on our common Digi embedded Yocto and Android software platforms. Digi has invested heavily in security, and we provide a full framework of production-ready security features called Trust Fence, enabling customers to build secure connected devices without extra cost or time needed to add security into their products. DigiSoms fully integrate Wi-Fi and Bluetooth connectivity, and they are also integrated with our range of XP RF modules, providing even more flexibility with broad support for leading IoT standards like LTE cellular, mesh networking, and long-range sub-gigahertz. And Digi is a global organization providing exceptional global technical and commercial support, as well as design services to help customers to accelerate their projects. And that's it from my side. Thanks a lot for the attention, and over to Sam.
Introduced me, so I'll save you from that. But as you can see in this introductory slide, we offer a very wide variety of thin film amorphous panels, custom shapes and sizes. And what I primarily work on is making PV cells that fit into IoT devices that supplement power. And that's what I will be talking about today. So a quick overview of PowerFilm. Again, we design custom solar cells, modules, panels, and power solutions using our thin film proprietary amorphous silicon solar. We also use high efficiency crystalline or gallium arsenide, really application dependent. So whatever technology is best suited. We've been in business for over 30 years, starting out providing rugged solar blankets to the military, U.S. military, also rugged solutions to transportation industry. And then throughout that time, we've developed the smaller, more modules that are really well suited for IoT. I like to say that we have been providing solar for IoT before IoT was even a thing. We have one facility located in Ames, Iowa, and a lot of our customers value the fact that we are 100% U.S. made. And the concept of energy harvesting and power efficiency are very, very closely related. As Martin was talking about, there's so many different tools and so many different ways you can optimize the power of your device. And every optimization is just going to make that energy harvesting solar solution work that much better. I worked on a project where we changed one word of one line of code and it increased the power consumption by 100x. So if you have a energy harvesting solution defined and it's ready to go, and then your software guy comes to you and says, hey, I have this update, but we're going to need 100 times more power from the solar panel, that conversation might not go over super well. So it's really, really critical for every single step of the development process to consider power efficiency, every component of software, every component of hardware. So it's really great to learn and know about the tools that are available that are enabling these ultra low power devices. We're seeing a lot of interest and adoption of energy harvesting solutions to solve battery related pain points in the IoT market. You might have seen Samsung recently launched a solar powered TV remote. Very cool. They claim that it will save 100 million AAA batteries over 7 years. So you can see that's just one example of how power efficiency and thinking about power solutions in a different way can have a large impact. Some of the low power applications that we focus on that energy harvesting is a good fit for are Bluetooth beacons, wireless sensors, ESLs, price tags, wearables, telematics, lots of ag applications. We work with a lot of smart locks, and really any low power electronic that you could run on a battery is a potential device that could benefit from energy harvesting. So Martin talked about tools for optimizing power of your device, and I'm going to talk about how you optimize your power source for efficiency. So when you look at a power source, you can break it down into several components. You have your power management circuitry or power management IC. You have a storage element, for example, a lithium battery. You have your load, which is your low power electronic or your device, like a Bluetooth sensor. And then, of course, you have your harvesting element, such as a PV cell. And you might ask yourself, which is a great question, where does the power loss occur? Where are my inefficiencies at? Each component is going to have some sort of intrinsic power loss or inefficiency. So it's important to understand what the dependencies are. For a power management circuit, that's going to be quiescent current. A standard modern energy harvesting power management IC is going to draw in the neighborhood of 400 nanoamps to 2 microamps just to run. If you're looking at standard chargers or even a standard solar charger, it's going to be a lot higher power consumption, 100 microamps all the way up to 40 milliamps for some larger systems. Batteries have intrinsic leakage. So a lithium ion type, you're going to see 1 to 2% leakage per month. Supercaps, a smaller or moderately sized supercap could have 1 to 2 microamps of intrinsic leakage. For storage elements, that's going to be dependent on size. So if you have a larger storage element, it's going to have a higher leakage. Oftentimes, your device or your low power electronic will require a constant voltage supply. So you may need some regulation or some converters to do that. And that could run anywhere from 85 to 95% efficient. And then, of course, your energy harvesting elements, such as a PV cell, especially in an indoor environment, is going to oftentimes be low voltage. So to get that up to your battery voltage of 3.7, you're going to have to do a DC-DC boost, and that can be anywhere from 85 to 95% efficient. So my laundry list of tips to optimize all these components would be matching your battery or your supercap capacity to what you need in your application. You don't want more than you need, or else you're going to have more leakage, which for some of these very, very low power devices can be very significant. You want to match your PV voltage to your storage element. So the less work your DC-DC boost has to do, the more efficient that process is going to be. You're going to be sitting closer to that 95% versus 85%. And then a lot of applications, and like Rich was saying, it all depends on the application. Sometimes you can cut out these middlemen and you can maybe cut out the battery. You might cut out the output buck, the output converter. You could cut out the PMIC altogether. And every component you cut out, you're cutting out that little bit of power loss. If you do need those components, such as the steady state output supply, if your battery is over 500 millivolts over your load, you should opt for a DC-DC buck converter over a LDO, which is going to be a much more efficient process. And then using shielded inductors and mega ohm range resistors can also have a large impact on your system efficiency. For this specific dev kit, using unshielded inductors actually reduces the efficiency of the boost converter by 10 to 15 percentage points. So if you want the trade-off for a lower cost inductor, you can make that trade-off. Or if you want to optimize for efficiency, definitely choose the higher quality parts. Skipped ahead. So looking at the individual components of our system, the energy harvesting power management IC is going to be your central device, managing the power from all the different components and making sure the system operates efficiently. It doesn't necessarily have to be an IC. It could be a combination of passive or active components that are completing these functions. But there's going to be several critical features, and then what I like to call bonus features, and then some kind of common sense considerations. So a PMIC should have some sort of overvoltage protection. Solar cells have a very wide active output voltage range. And if that needs to be controlled so that it doesn't do something like damage a battery by overcharging it. So your PMIC should have overvoltage protection to stop charging your battery at a predefined termination voltage. On the other side, you should have undervoltage protection. So you should be able to have the capability to disconnect your load or indicate to your load that they need to go into an ultra low power state to conserve your battery and not to damage it by over discharging it. Low voltage input is very critical for energy harvesting solutions. Oftentimes, and we'll discuss this later, you want a single cell PV, which could have an operating point below 1 volt. And it's very important to be able to boost that up to your storage element voltage, 3.7 or somewhere in that range. Cold start is also a critical feature for batteryless applications. If your system runs on capacitors or supercaps, and is very possible in its use case that it gets drained completely to 0 volts on a regular basis. And it's important that whatever circuitry or PMIC you choose is able to efficiently charge the system from 0 volts. Some PMICs have great algorithms for doing that. Some have poor algorithms for doing that. Others don't support that at all. So it's important to know what your functionality is. Some bonus features that are really convenient for specific applications: primary battery backup, those DC or LDO outputs, supercap balancing. If you have a supercap that has multiple cells in it, you want to make sure they are all balanced. Status pins, again, communicating back to your central MCU saying, hey, here's the status of the controller, everything's working good. And then configurable presets, maybe a couple pins on the package where you ground them, and then voila, your system is set up to charge a lithium battery. That can really save on external components. And then those common sense considerations: footprint. Do you need the layout to fit in a super compact wearable? Are you working with a thermostat where maybe you got a little bit more room to play? Cost, external components. So those are things that you should consider when for the energy harvesting power management. There's lots of different storage elements that you can choose from. Most common is going to be just a lithium battery. A standard lithium battery has high power density. They used to be relatively available until the EV market decided that they wanted them all. They got relatively low leakage, 1% to 2%, which is manageable as long as you, again, size that battery appropriately. There's high performance lithium technologies that have ultra low leakage, ultra long lifetime, and then extended temperature range. So if you need that industrial minus 40 to 85C, they got you covered. If you're trying to get away from lithium, which is what a lot of people are trying to do, capacitors or supercapacitors can be a great choice. Even a simple standard surface mount cap is capable of powering a low power RF module for a short period of time on the range of 30 seconds or so. They're size limited, of course, but they have negligible leakage. We have several reference designs and dev kits that show how you can power a Bluetooth sensor off of surface mount caps. If you want longer runtime, you could opt for a supercapacitor. If you want hours of runtime or days or maybe even a week, you can get you can use a super cap. They're going to be a little bit larger size, more similar to a lithium polymer type battery. But again, you get that longer runtime. Another cool battery technology is solid state. It's going to have similar functionality to a super cap where you could run for those days or a week, but it's going to be ultra compact. And it comes in a surface mount package, which is very nice. They have pulse currents that can drive RF modules, RF radios, sensors. So that could be a really nice solution for if your application requires that. I also threw nickel metal hydride up here. I don't think it gets enough love. We got a couple customers that are using that. They're relatively simple to charge. They got low leakage. They're pretty low cost. And they can be really convenient if you already have a device that is packaged for AA or AAA batteries or another common battery size. Choosing the right PV cell is also very important when you want to maximize efficiency of your system. A lot of people just look at nameplate efficiency, which may be important for, like, say, solar on your rooftop or solar at a utility scale. But when you're talking about IoT applications, portable devices, it really doesn't mean anything. If you look on the graphs on the right side, you can see how spectral difference and light intensity can basically flip solar efficiency on its head. Under an LED spectrum at low light intensity, amorphous silicon, even though it has the lowest nameplate efficiency, produces the most power. And ironically, triple junction gallium arsenide produces the least amount of power, even though it has the highest nameplate efficiency. So really changing the spectrum of going from outdoors in the sun to indoors under an LED light is going to have a great impact on the performance of a PV cell. And then that light intensity going from direct sunlight down to 200 lux, which is almost 1,000 times less intense, has a huge impact on the performance of a cell. If that cell or that module is not designed to account for performance at low light, minor material defects that normally wouldn't matter become very prominent and can render most PV cells inoperable or perform very poorly. So the bottom line is you want to source a PV cell that is rated and optimized for your expected light conditions and environment. So can cell configuration affect output? Of course it can. So a PV cell can consist of one or more cells connected in series. And we know from Kirchhoff's law that any point on a single branch of a circuit has to have the same amount of current. So if you have one cell that is shaded and you have a multi-cell panel, all of the other cells are going to perform as if they were shaded. So for applications with irregular lighting, such as wearables or portables or really any indoor environment, a lot of times indoor environments have very irregular lighting conditions. It's better to opt for fewer cells or a single cell PV module to mitigate and actually completely eliminate shading effects. Since anywhere on that PV cell, an electron is always going to find a way to get from positive to negative. So the picture shown, if you cover half the module, a multi-cell panel, the output could be 0. But a single cell panel, you're only losing that portion of the panel that's covered or shaded. Similarly, with curved objects, curving a panel around an object, you're going to get those shading effects. It's also worth noting that larger cells are more spatially efficient since they don't need that interconnect area. Every time you add a cell, you're adding dead area where the PV has to interconnect. The boost efficiency of a single cell is going to be lower than a multi-cell, but it does offset a little bit from that spatial efficiency. And for certain applications, you have to go with the single cell. There's no question. So that 85% is still pretty good. So kind of putting everything together, here are 3 use cases that sort of describe how you might choose different components to maximize efficiency. So case number 1 is an inventory tracking application where you place gateways throughout a warehouse, and those gateways track tagged items in the warehouse. As it's a gateway, it's a little bit higher power consumption, but you're able to offset that by installing the devices directly under lights to provide that higher power. Since we're installing directly under lights, the lighting is very regular. We can eliminate the battery since the lights are on 24/7 and the device only needs to work when the lights are on. We can eliminate the PMIC because since we have that regular lighting, we can use a higher voltage panel. And then we just throw a super cap in to stabilize everything. And then that results in a total system efficiency of 93%, which is just the diode drop across from the solar to the system. So that's a good case where you can eliminate a bunch of middlemen and get a very efficient, low-cost, simple system. Case number 2 is a pet tracker, a wearable device with an integrated PV cell. Since it's a wearable and it's curved around a surface, we're going to see a lot of irregular lighting, so we're going to opt for a single cell PV. We want the device to be able to operate when there's no light present, so we're going to throw a lithium battery on it. And then let's just say that that device requires a constant voltage to run. So if we have a standard energy harvesting PMIC to boost that single cell up to 3.7, that's going to be 87% efficient, and then 95% efficient from battery to load, which results in an overall system efficiency of 83%. You might think that is a little bit low, but if you try to incorporate a multi-cell panel to increase that efficiency, that irregular lighting and shading effects is going to render that panel inoperable in a large percentage of the use case. And then finally, an electronic price tag. Retail environments are very bright and have lots of devices that could potentially use solar. So the price tag is a really great use case. The lighting on the edge of a shelf is pretty regular. You don't run into a whole lot of irregularities. So we can use a 3-cell PV design to optimize efficiency of the boost converter. Then let's say we can directly power that device from the battery, and we'll use a standard energy harvesting PMIC. So the overall system efficiency is 95%. So here are 3 cases where the application requirements are very different, and the PV and the power management solution is very different, but you're still able to get high efficiency. My last slide, real quick. If you want to get started with energy harvesting, we got a lot of tools on our website, development kits, standard products. If you want to learn more, we have a technical blog that answers lots of common questions regarding PV and energy harvesting. So I'd encourage you to check that out or reach out. And I believe I will be handing it back to Rich for some Q&A. Thank you.
You believe correctly. So this is the time when we answer your questions. So as I said earlier, enter them into the question box and we will answer as many as we have time for. Sam, before I let you go, and before I forget what I was thinking, you said 2 things that I want clarification on. One is that you use the term shading often. Do you mean literally shading? You know, if there's a shade over the cell?
Yes, literal shading or covering,
Okay.
Either one.
Okay, I didn't know if that was some technical term that I missed.
Nope, literal light shading.
Okay. And then the second one, you said something about adding a super cap, and you use super cap and low cost in the same sentence. Is that valid? I mean, when you add a super cap, isn't that relatively expensive to the system that we're talking about?
It depends on the size and the capacity and the form factor. So when comparing to like a standard lithium battery, it may be comparable, but it's not going to be like 5 cents. I guess that's how I'd answer that question.
Okay. Very good. Okay, Martin, you are my next target here. So let's give you the first question from the audience. How easy is it for a developer to create a battery-powered solution with a DigiSOM?
I would say it's a normal task in the development and in the integration of the SOM to a custom baseboard. We provide full documentation for it. So we provide schematics, and there's even a nice comparison in our documentation portal between how you would develop a mains-powered versus a battery-powered devices with comparison schematics. So you see both use cases quite nicely, and it's one of the steps for a normal integration. It's not easy, so to say, but it's also not difficult. So I would say it's absolutely doable, and we provide the documentation to do that.
Okay. This one probably goes to Sam. The question is, can any photovoltaic cell be used with an off-the-shelf energy harvesting PMIC?
Great question. I guess, like I was saying in my slide on efficiency, first and foremost, you want to make sure that your cell is optimized for your environment. So if it's an indoor environment, you want an indoor PV cell. And then also you want to make sure that your voltage of your cell is under the max voltage of the PMIC, which is often 5 to 6 volts. There are many cells available that if you take them outside, they might be very high voltage and could potentially damage your PMIC. So there's a couple of considerations when choosing that not all off-the-shelf PV modules are compatible with standard energy harvesting power management ICs.
Would you take that one step further? What's an indoor cell as opposed to an outdoor cell? Isn't light and a cell a cell?
Light is light, but when you are reducing light intensity by 1,000 times, technology doesn't work the same way. So if processing and manufacturing steps are not optimized to reduce those material defects, then a cell may have very, very, very low performance, even lower than you would 1,000x. It could be very close to zero when you take it from outdoors to an indoor environment. Also, that spectrum change, some PV cells require certain components of a spectrum, and if those components are missing, that panel will just cease to operate.
Okay.
So,
but aren't there applications where you don't know if you're going to be indoors or outdoors?
yes. So those applications, you got to dance around it a little bit, and definitely choose the technology that's right for that. But there's usually some tricks that you can play to get around. You usually would choose an indoor technology, and then it also works outdoors, but you got to be careful about it.
Okay. Very good. Thank you. I don't mean to pick on you, Sam. Sorry.
I love it.
Let's see. I think this is for Martin. Are there any other applications where you think power efficiency is crucial apart from the one you mentioned? I think it was you who mentioned that. So.
Yes, I mentioned a few. I think in demanding industrial applications and medical, but I would say those were just two examples. It's across all of our customer base that power efficiency and power management is a topic. We do have also a lot of customers in the solar area, which I would mention, but maybe to also mention a few others. Logistics is a big topic, like, for example, warehouse monitoring. The devices, they all get wireless now and mobile. They have to move around, and you have robots and so on in warehouses. So that's a big market, I would say, where we see a lot of discussion about power management, power efficiency. And maybe one more to mention is transportation and agriculture. For example, in agriculture, where you have these harvesting machines and tractors and so on, there's so much technology in those devices nowadays with GPS and high precision location, and farmers can move around with the device in their hand and not being in the tractor and so on. So it's a lot. There's a huge technology explosion in that area, and in this market, it's also a key to talk about power efficiency, of course. If there's anybody in the audience who has a specific application in mind and wants to talk about that, contact us and we can discuss that. So it's always nice to discuss customers' applications, of course.
So here's my application, Martin. I'm here in Florida, and it's hot. It's really hot, when it ends out in the sun. How does that play into this? Am I just going to melt my cell?
Is that a question for Sam?
Probably, but you were talking about applications, so I was directing you. I don't care who answers it. Is that a big issue, that these things get super duper hot?
In general, I would say not. I mean, I can speak about our solution. It is fully industrial temperature graded, so it can take up to 105 degrees CPU temperature, typically 85 degrees ambient temperature. So they are pretty tough in that regard. And of course, we have customers with very demanding applications where you need to have some kind of airflow in the system. And we actually have only just a very few customers who use fans and so on our solutions. The ARM-based processors and also our XP modules, they are quite heat efficient, I would say. So you typically don't have so much heat generation in those solutions. So it's very rare to see customers using fans. So typically passive heat dissipation, heat sinks and so on are fine. So I wouldn't see a problem in your application.
I assume you're referring to Celsius numbers, right?
Yes.
Okay.
Sorry. Correct.
Sam, do you concur?
Yeah, I mean, it's very application dependent, and that's part of what we do here at PowerFilm is customize the PV cell to meet the environmental requirements. I mean, applications that come to my head are semi-trailers where the panel might be mounted behind the exhaust of a reefer unit. So you might be seeing those 85 or 100 degrees C temperatures, and we need to customize the panel to be able to handle that. I mean, in a lot of times the indoor environments are a lot more generous. Don't need that 85C. So maybe you can get by with some lower cost laminates and encapsulants that can save you some money. But yeah, it's very application dependent.
Okay. I think you just answered this, Martin, but just to be totally clear, somebody in the audience asked the question, can my own app monitor the temperature and then command the CPU frequency.
Yes, absolutely. So it is possible if you have low-level access to the system, and it's more convenient on the Digi solution using this APIX programming interface I mentioned. So from there, it is possible to do that directly from your application in actual application code without requiring to go to the system level.
Okay. And then along those same lines, what do I need to do to go to the low power mode in the Connect Core modules?
Oh, that's actually a very good question, because normally that's not so trivial, because you have to take care that all the components of the system, like wireless, you want to handle the connection properly in a low power state, coming back and reconnect, or file system. You don't want to cut power when you write a file, obviously. So you have to handle all these things, and normally this is done in a manual process. And in the Connect Core solution, we have in our offering we have several scripts to support customers with that, and it's basically in the end just calling standby, and all the components that are required to be handled are handled by that script. So it's quite convenient in our solution.
Very good. Well, gentlemen, I'm afraid that is all we have time for. I'd like to thank both of you for awesome presentations. I'd also like to thank Digi International and PowerFilm Solar for sponsoring this event. And of course, we can never do these things without you, the engineer. A final reminder that all Open Systems Media webcasts are copyrighted and may not be recorded without prior permission. So thank you all for attending, and I hope you have a great day.